In this video, we'll discuss volume. Now, the volume is the amount of space a solid occupies. And it's important to recognize that just like when we can use the moving additivity principles with area, we can also use them with volume as we may need them. We also have Cavalier's principle about volume, and this states that a solid that's been sheared has the same volume as the original solid. Well, what does that mean? Well, the thing that we're thinking about with the sheerness is when we construct oblique solids. The key is that the sheerness just means they've been slanted and they still have the same height and the same other area of the base. So the pieces are the same, it's just that fact that it's been kind of slanted away from the right solid. A way to think about this is if we had a stack of quarters. As long as we keep the stack the same height, we can push the quarters left and right and make the column look funny, but each individual quarter has the exact same volume and they're the same height overall. Therefore, this left and right column would have the same volume for that stack. Now we have common volume formulas that we do use to help us find the volume of different solids. With prisms and cylinders, we use the area of the base times the height. If it's a pyramid or a cone, we'll take 1/3 times the area of the base times the height. And if it is the volume of a sphere, it's 4/3 times pi times the radius cubed. Now, one of the things you'll see in different places when you look up these formulas is a capital B or a lowercase b. If it is a capital B, that represents the area of the base. A lowercase b represents just the length of a single side. So you may see those two letters. Recognize capitalization matters, whether you're finding area or determining just the length of a side. So let's look at these two solids and determine what would be the faces that would represent the base and the segments that represent the height for each solid. That's a very important thing to understand to determine how to use the formulas. Remember, the bases are the polygon for which pulls through the entire shape and is parallel to one another. So when I look at this first one, I see that the front and back side is both triangles, and when I pull it through, it maintains that shape from the front to the back. That means that the bases of this solid, which is a triangular prism, would be a triangle ABF and triangle DCE. The three segments that connect the two bases would then represent the height. So I could use EF, CB, or segment AD to represent that height, depending on which one I may have the measurement for. When I look at my right solid, I see that the front and back are pentagons. And if I watch and pull that pentagon through, it maintains that shape. So that means that this is a pentagonal prism with the bases being MNPQR, and the back one would be HGKJL. And then the 5 segments would then represent the height that would connect those two prisms. And that would be segments RL, HM, GN, PK, or JQ. Now, once I can recognize and identify the solid, and then I can identify the base shape of the solid, I can then work on trying to calculate the volume. I can first calculate the area of that base shape, recognize what is the height, and then plug those two pieces into the generalized formula to calculate volume. So say that I have here that I want to calculate the volume of the cylinder. So the key thing is that this is a cylinder. That's identifying that solid. I recognize that the base shape is a circle. So the front and back sides are circles. And then that tells me that to find the area of the base, I would be following the area of a circle, which is the radius squared times pi. In this case, I'll be looking then for the volume of the cylinder to be the area of that circle times the height, the segment length that connects the two circles. So in this case, the radius squared times pi times h. The radius is 6 inches. The height is 14 inches. And here you can see I've used the commutative property, swap them around so I can multiply the numbers and then have pi on the end. So this becomes 36 square inches times 14 inches times pi, which is 504 pi cubic inches because I have inches squared times inches. And that's about 1,583 cubic inches. Now let's look at the idea of a pyramid. So sometimes we have to calculate those pieces that we may need to help us determine the volume. So say the students are building a right square pyramid for decorations at a school dance. Each triangular face of the pyramid is 6 feet wide and 5 feet tall. Once constructed, what will be the volume of the pyramid? So the first thing to think about is, what should that look like? Well, if I have triangular faces that are 6 feet wide and 5 feet tall, and I'm going to construct them into right square pyramids, laying down, it would look like this. This is the net for the square pyramid. Then I would want to raise those sides up and say that, okay, here is what I have. And when I look at the square pyramid in this case, I can see that I have the length of one side and the slant height of my square pyramid. So now I can start to think about, well, what do I have? Again, I have a right square pyramid. So I'm going to use the formula that I'm looking at 1/3 the area of the base times the height. So I need to determine what's the area of the base and what's the height. The area of the base, since it's a square, would be 6 feet by 6 feet, which is 36 square feet. What's more challenging is the idea of the height, because the height goes from the center of my square pyramid up to the apex, because this is a right square pyramid. So I have to calculate this and think about, what do I have? Well, if I draw from the center to the edge and from the center to the apex, look at what shape that constructs. That is a right triangle. And what I have to recognize is that from the center to the edge is half the length of one of my sides of my square pyramid. So that is 3 feet, and then I have to calculate my height. Since it's a right triangle, I can use Pythagorean theorem. So the height squared plus 3 feet squared will equal 5 feet squared. So that tells me that the height squared plus 9 feet squared equals 25 feet squared. And then I will subtract the 9 and then take the square root so that I can get back to just the heights measured in feet. So the square root of 16 square feet is 4 feet. So now I can look at and put it all together. I have 1/3 times the area of the base, which we found to be 36 square feet, times the height, which we just determined was 4 feet. So 1/3 of 36 is 12 square feet. 12 times 4 is 48 cubic feet. So here, I wasn't given my height originally, but by using the right triangle, knowing that this is a right square pyramid, I was able to calculate that final measurement that allowed me to determine my volume.